So now we're going to talk about another asymptotic notation. So previously we've talked about big O, which is an asymptotic upper bound. Then we've talked about big omega, which is an asymptotic lower bound. So now we want to have a notation that represents asymptotically tight, meaning that it matches the exact order of whatever specified for that complexity function, at least on asymptotic terms. So we're going to talk about big theta. And the way I like to remember that this is the one that is for asymptotically tight is it looks kind of like a big O, but it has the theta, because it's a theta symbol, like it's just theta. But the thing is, it looks like big O, but it has a line through it, so just a straight line. It's almost like it's tight, you know, it's on the same order. So very often when you talk to someone, it says, if I give you two complexity functions, f and g, and they say f is of order g, they usually mean this. They usually mean this. So for example, if you were dealing in big O terms, which I'll show you what I mean in a moment. Let me just get to the definition. So suppose I have two complexity functions, f and g. We would say that f is big theta of g, if and only f, if and only f. So remember, everything that comes just before the if and only f, this is true, then whatever comes after has to be true. If that's false, whatever's here has to be false. They're equivalent. If and only if f is big O of g, and f is big omega of g. That's it. So my definition of big omega here that we've presented here for us. So our definition, this one is actually a combination of two definitions. So if you understand what big O is, and you understand what big omega is, you understand what big theta is. So let me give you an example just quickly before we get into like trying to use this definition for trying to prove a claim, is why you might consider big theta. Now suppose that I gave you a function that I say this represents the number of operations that occur in an algorithm in the worst case. Say for example, so let me just give you an example of usage here. So say if I give you a complexity function, it looks like this, like 2n plus 5n cubed plus 2. Say if I count up all those operations in my algorithm in the worst case, I derive this guy right here for f. What would you say if I wanted to come up with the most asymptotically tight big O here? So a tip I can give you when it comes to big O notation is that you can drop these multiplicative constants and the additive ones, and then you look for the highest degree polynomial, because we have a constant number of terms. So if it isn't in that form, I recommend you do some more algebra playing around with it. So what you can do is you can show that this right here, this is big O of n cubed. So you can show that that's big O of n cubed. But what's also true mathematically speaking, there's that M word again, the mustard and mayonnaise, making a good sandwich here. You can also say that this is also big O of n to the 99. This is also true. It's not very accurate of a statement about the running time of that algorithm, but it is a true statement. So when you pick up big theta is, as I suggest, asymptotically tight, meaning that the asymptotic lower bound from big omega and the asymptotic upper bound from big O, they're both satisfied. So there's going to be some sufficient point for n0. In this case, there's going to be now two constants, and there's going to be this case where now you're going to show that they're actually matching the same asymptotic order. So what you can say is that this is big theta of n cubed, but you cannot say that this is big theta of n to the 99. This is not true. It is not big theta of n to the 99. Likewise, if I were to give you an algorithm, say like binary search. Binary search runs in big O of log n time. Right? That's what you very often hear about binary search. it's also true because if you actually look at its complexity function, you can also establish that it is big theta of log n time. But you can technically, like I just said here, you can also say that binary search runs in big O of n log n time if you wanted to. You can say that. That's actually not incorrect. If you actually are picking up the definition, you use it. That is not a false statement. It's an inaccurate statement, though. So this is actually true, just like that's also true. But the thing is, this is not tight, right? This is not asymptotically tight. So very often when you actually analyze the running time of an algorithm, very often you try to derive a complexity function, you analyze it so that you can obtain a tight asymptotic result. So you're normally, when you analyze algorithms with big O, you're almost always actually trying to achieve a big theta bound like this. So you're actually trying to obtain a big theta result. Just nobody's told you this up to this point. Just the other reason why that you haven't is probably because you haven't seen big omega. But if you ever are unsure, just pick up the definition for big omega and you can establish it after that, okay? So this is how you could use big theta. It's meant for if you're trying to say, yeah, it's actually just, it's this asymptotic order. So it's asymptotically tight. So it's not asymptotic lower bound, upper bound. It is both of them. It's not one or the other. It is both of them. So this is asymptotically tight. So this is the kind of thing you desire when you use big O notation in the first place. So now that we've talked about that, we have a definition for big theta. Let's do an example. Now, as I've suggested with our definition, it's really that if I want to prove a big theta claim, it's that I need to establish both of these things together. So these both have to be true. So if I'm actually studying and trying to show, hey, look, is this function, remember, this is a statement about functions, right? So I want to establish that f is big O and f is big omega of the other function. What does that mean? I can either prove those claims separately, but show that both of them are true, or I can attempt to take this definition and I can just sort of expand it so that I do it at the same time. So I'm going to try proving them together at the same time, but I advise that you take and break it into two parts to convince yourself that I've done the same thing. So here, let's do an example. Let's prove that 3n cubed plus 5 is big theta of n cubed. So what I'm going to do is, just to make this easier for myself, is I'm just going to try to identify one integer constant, and I'm going to have two positive real constants. If you want to have two separate integer constants, that's okay. I'm just picking the largest of the two values that would be your integer constants in this example. So just be aware of that little detail. So proof. We find constants C1, C2, which are going to be positive real constants. And we're going to find an N0, which is going to be a positive integer. Just as a remark, I'm just going to take so I'm taking the max of two integer constants. So you would have, for example, an N1 and an N2 to match up with the C1 and C2, okay? But that's not, this is just a remark. And N0 such that for all n greater or equal to N0, it has to be that C1 times n cubed is less than or equal, remember this is the big O part of the definition, is less than or equal, is it the big O or big omega? Well, let's write this out. And let's see what happens. So this is F right here. That's G, right? So maybe maybe you have to be a bit careful here. Yeah, so if you look carefully at this, and I misspoke earlier because I want you to think about this. That's the whole point. So notice here that if you actually take this and you rewrite this the other way around, you'll notice that this is saying 3n cubed plus 5 is greater or equal to n cubed times c1, right? That's the big omega part of the definition. This right here is the big O part of the definition. So I've just chained them together as one longer set of inequalities. So again, like I've said previously, you can always try proving this separately. If this looks a little too complex, just take it apart, just pick up the definitions of each one separately, and just do it that way. So you might look at this and pick up one of the strategies that we've done previously. So for example, notice that I have something that's like 3n cubed plus a 5. If I can make something that looks like something in terms of n cubes that looks like this, but definitely will be larger than this, or matches it for all n greater or equal to 1, then we're okay, right? So I would like to do something on this side that matches that. Likewise, I would also like to get a nice lower bound on 3n cubed plus 5 by trying to get something that looks like n cubed, but doesn't necessarily match the total size of this. And keep in mind, I could try to do that if I wanted to, but I would like to get a lower bound on it, as opposed to an upper bound like I was over on the right-hand side, or the rightmost inequality, to be a bit more precise. So what I'm going to do is I'm going to use my lookalike approach. We're going to pick C1 to be 3 and C2 to be 8. Now remember, the game plan is to find these constants, right? And we have to then show that they actually are correct. They work. We don't have to show all of them. We just need these constants to work. So I'm going to pick 3 and 8 because 3n cubed is less or equal to 3n cubed plus 5. It's just the same thing as this first term, and this has a little extra, right? That's okay. 8n cubed would be like, if I had 3n cubed, that would take away 3 from the 8, which would be leaving with 5n cubed. And for all n greater or equal to 1, 5 would be less or equal to 5n cubed, right? That's sort of the mentality I'm coming in at this with. So pick those constants. Then we find n0 so that for all n greater or equal to n0, it has to be that 3n cubed is less than or equal to 3n cubed plus 5, but this also has to be less than or equal to 8n cubed. So we're going to take it in chunks just like I did before. So we're going to look at this part, then we're going to look at that part. If we can do that, then we're okay. So first, on the leftmost inequality, notice that 3n cubed is less than or equal to 3n cubed plus 5 for all n greater or equal to 1, right? I think this statement is easy enough for you to see directly, right? Because there's 3n cubed and then there's a 3n cubed here plus a little extra bit. Nothing scary about that. Second, on the rightmost inequality, on the rightmost inequality, 3n cubed plus 5 is less than or equal to 3n cubed plus 5n cubed, which is equal to 8n cubed for all n greater or equal to 1, and we're going to use our bucketing argument that we had before. So watch this. As 3n cubed is less than or equal to 3n cubed for all n greater or equal to 1, and 5 is less than or equal to sorry, 5 is less or equal to 5. I was about to say 3, but it's actually 5. 5 is less or equal to 5n cubed for all n greater or equal to 1. So now that I've shown you that I have 1 for the leftmost inequality, I have 1 for the rightmost inequality. So it means that if I take the largest of those values, which I must stress that if I wanted to have an n1 and an n2 instead of just a single constant like that, I would take the maximum of those two things. So in this case, I'm just going to choose n0 to be 1. Therefore, by the definition of Big-Theta, 3n cubed, that n's looking a little sad. Let me fix it up. 3n cubed plus 5 is Big-Theta of n cubed. And that completes the proof. So the box just indicates the end of the proof. But yeah, so now that we have a family of different asymptotic notations, now we actually have a way of saying, okay, these are all of the linear functions. We have all the quadratic ones. We have the cubics. We have the constant functions. But we have to be a bit careful when we say that kind of stuff because when we talk about Big-Theta, Big-Theta now is a statement about O and omega, not just O. But yeah, that's Big-Theta.